So let's start today's lecture, the second one in geophysical flows. So I am Anirban Guha, I am an assistant professor in mechanical engineering at IIT Kanpur. Probably most of you have attended my first lecture. So this one, so knowing that most of you are from IIT Kanpur, I will pitch this one at the difficulty level of this one will be slightly more than the one. Like the last one was quite introductory, although I won't say that Boussinesq approximation is something which is easy. It is easy to implement, but difficult to understand, slightly difficult to understand. So please go through it, go through my notes and the notes which are online. Okay. So today I will start with something. So yesterday you came to know about Boussinesq approximation, that is the density of ocean or atmosphere in general of geophysical flows is not constant, it varies. Okay. And the one which Professor Huppert showed, it had it is an unstable stratification. You have heavy fluid on the top and a lighter fluid in the bottom, and the experiment you have seen that the heavier fluid tries to come down. It is an unstable stratification. In oceans, it is obviously unstable situations do arise, but the ocean is largely stably stratified. So, for example, if I have to draw the density, so this is the ocean's bottom, say, and is the top surface, and if I have to draw the density, it goes like this and say. So the mean density profile somewhat looks like that. Okay, I mean, so there is a region where the density changes sharply. This region is called pycnocline. It's a good name to know. The density changes. Okay, and so if this is my x and z, density. As you go down, the density keeps on increasing. Okay. So this is a very important research done by this group. This author's name is Polzin, who showed that. So this is basically the Midatlantic Ridge. Okay, and this is more of the plains of Brazilian basin. Okay, it's down here. It's like 3,500 to 4,000 meters deep. Please note that the horizontal axis is longitude. Okay, you see that in this region there is almost no turbulence activity, which is kind of measured by this diffusivity. This is not your normal diffusion, this is turbulent diffusivity, this is a vertical eddy diffusivity, which shows that there is a lot of thing going around here, okay, and almost nothing going around here. Okay. And obviously this cannot be a boundary layer effect, because this is happening far above the boundary layer. Boundary layer would be, you can say, it's very close here. Okay. And this slope, although it looks like how much, 20 degrees or something, is absolutely not. It's 0.1 degrees, because this is longitude. I mean, I have done the calculation. It's like 0.1 degrees. It's almost like this, slightly more than that, but yeah, it's almost very flat. But here you will see, and also it's not like this sharp. It will be spread out, so it's like a mountain. Okay, so these things are happening in the Mid-Atlantic Ridge, and people do understand, and that actually spurred a lot of research on internal gravity waves. So people understood that something which is definitely not boundary layer, and people understand internal gravity waves to some extent, that they are causing this. So it's like the long waves are, so there is like a this is something called a parametric subharmonic instability. So the longer waves gives its energy to the smaller, like the shorter daughter waves, and these kinds of cascades, and then that finally breaks down into turbulence. So it's a nonlinear energy transfer that happens. and that spurred a lot of research. So yesterday I was saying that so the abyss, the deeper ocean is quiet. It can be quiet if nothing, the bottom is the bottom slope is not that much. If the bottom slope is more than a critical slope or is more rough, then you can expect certain things, and there are spots like this in the ocean. Okay. And it is expected that why it is important, because here you have enhanced turbulence that causes mixing. So the tides cause, the tidal energy finally causes ocean mixing, and people were always thinking where does it happen, and deep ocean was kind of out of the picture initially. Okay. But it turns out that the deep ocean at regions, at the pockets, it is very important. People initially thought that it is mostly in the coastal oceans. Yes, it is important, but also in the deeper oceans it is important at patches.
What is the order of height of those mountain ledges?
So you can see that it is 5500 and this is 4000. So it depends. I mean, it's like 1500 meters or something right here. Okay.
A large ship like Titanic which has sunk to the bottom of the that doesn't that would be
it collided with an iceberg, right?
No, once it settles on the seabed.
Okay.
That is more or less like a rough terrain or sudden.
That is somewhat of a rough terrain. Yeah, but that length scale is, whether that length scale is enough to trigger some, I mean some internal gravity waves, it will trigger, but the angle also is very important. The slope, what it creates, the shape and the slope, that's also very important. Okay. So from there, it is just a motivational slide, and this is something which my student gave me. Okay. So this is a continental shelf. Okay. So it's like the continent starts from here, from the ocean, and this is it is now understood very well that if this angle, okay, the angle of the continental shelf or the mountain, if it matches with the internal gravity waves, say it's a group's direction, it's a group speed, it's a group direction, then it causes a lot of intensification in this region. Okay. So say this is a tide has a velocity of say 0.1 meters per second, that gets 10 times amplified. Okay. This is a very something of a lot of interest for in geophysical flows. There are papers which has shown that experimentally has shown that there you will find roll ups and billows here that breaks down into turbulence. That would be interesting. And these are the two other things which I would like you to simply to see about internal gravity wave. So this internal gravity wave is being generated by this small mountain. Okay. And they are traveling up. The density is more or less like this. This is called this is the pycnocline where it hits, and then it also hits the free surface. Okay. So this is a very magnified view of the free surface. If you see, it is 10 to the power minus 4. It's just a magnified view. So it causes some undulations in the free surface, and what we have been trying to do with this is, you have something on the free surface, and the free surface has the signature of the internal gravity waves. Internal gravity waves are produced by density stratification. So is it possible to reconstruct ocean's density stratification from the free surface? Okay. So that has been a work we have done. So it is possible. It is possible to if you decompose the ocean into not like this, but you break down into parts, like linear parts, it is possible. Okay. And so it is the surface signature of internal gravity waves, and this is the signature at the pycnocline. Pycnocline means here. Okay. This is the pycnocline, right. So sometimes the wave can hit the pycnocline and can generate waves at the pycnocline also. So now focusing on the pycnocline, you can see that, oops, this is not important now. That can generate some waves, and the amplitude of these waves are usually larger, obviously larger than this one. Okay. This is obvious, these two simulations are not the same, but just to show that, I mean, you can get waves at the pycnocline too. These are interfacial waves, can be of very large amplitude also, and these are triggered by, so these mountains not only cause waves on the top of the ocean, at the ocean surface, which would be of very small amplitude. Nowadays some satellites can actually find the signature of these things. These are slightly more difficult to find from the satellite signature, but they have larger amplitude, by the way. I mean, anything at here, so that is being shown here, right? Yeah. Yeah.
So why are waves not traveling towards x equal to 0?
X equals, I mean, if the waves have a velocity like this, group velocity, the wave goes here, and think of this as a source like a something like a light source. Where is it going to travel? I mean, if it goes, it gets reflected and it goes in that direction. Okay. I mean, and this is a, if these were solid surfaces where it can reflect back, then it would have gone back. Otherwise, it just goes away from your domain, right? So that's what it is. Okay.
Water is kind of steady, right?
Huh?
Mountain that is steady.
Yeah.
How can it give rise to wave like?
Because of the tides. So the tides are causing water, stratified water, to move back and forth like this. So it's a semi-diurnal tide. Every 12 hours you have going like this. So that's what actually gives rise to waves.
Minimum height, right? Minimum height.
I mean, minimum height means of the mountain.
Yeah, not nice width. They are need of minimum.
So even a small mountain can also generate waves. It is so, I mean, it is not just about the, so it is more of this angle which is quite important, and if it is a small mountain, its height also matters. There will be wave, it will be very feeble. It is not that it will not give rise to waves, it will be very feeble. Okay. So the as you say, the tides go to and fro and cause this. Okay. Even without tides, you can get internal gravity waves. That happens over the mountain. The lee waves, you have heard of the lee waves. The lee waves do happen. I mean, the atmosphere is not doing this, but you still have lee waves, which are formed like on the lee of the obstacle. So density contours will become something like that. So this mountain is going to cause the density contours to deform, these isopycnal surfaces, and that is basically the signature of the lee waves, is stationary. While these are traveling waves, so this talk today's my lecture is on these waves, on internal gravity waves, right? So it's just a motivation for studying them. Okay. So right now, any other questions from this, or I'll just close this one so that it does not distract. Frequency in Professor Huppert's talk, but I will just want to go into it a little bit, because probably most of you have not heard of it was mentioned buoyancy frequency, right? You didn't mention Brandweissel. Okay. So as I said, that the ocean's density is like this. So take it as Z1, Z2 and Z3. Okay. So the question is very simple. What happens if you take a parcel here? So these are very close. Z1, Z2 and Z3 are very close, and you displace it by delta Z. Okay. So this parcel from here has gone here. What happens to it? So here assume that the density is rho 1, here at this level the density is rho 2, and at this level the density is rho 3. Okay. So you have taken this parcel which is at this location Z2, you have just displaced it up. So, I am just drawing the picture here. So, the ambience is rho 1 and you know that rho 1, right, because it is stable stratification, that is that has to be the case. And now that it has gone at Z equals Z1, the ambient fluid has a density rho 1 and the density of this fluid is rho 2, okay, and you know that rho 2 is greater than rho 1. So, what will happen? What do you think is going to happen? You have displaced a heavy fluid from here upward and now you are leaving it, okay. What will be its tendency? It will try to fall down, right, and because of its weight, and there is something also acting, it is buoyancy. Right, that is all it is. So, what happens? It will try to fall down, but because of inertia it is going to overshoot, it goes even further and then it reaches a region which is lighter, which is heavier, and it is, I mean, it is lighter, the region is heavier. So, the buoyancy becomes higher. So, that region gives it a kick, it goes up, and so it keeps on oscillating, and that is what the whole idea of Brunt-Weisseler frequency is. Okay. So, what happens if you have a density stratified flow? You just say, if you put your hand, say I am just making it up, and you do like this. So, as if you have caught this this football and you have dragged it down and you leave it, it is supposed to go up, okay, and it is just going to oscillate. So, let us see how that the buoyancy frequency is n comes. So, this has so let us simply write the Newton's second law. So, it has been displaced up, okay, and so we will simply have this as rho 2 times V. So, becomes mass times this, and what is the what should be the upward force? Then it is rho 1 minus rho 2 G V, okay. Okay. So, the V V cancels, therefore, so now you have come to this point, okay. Now can we write rho 2? Now let us let's keep rho 2, let's write rho 1 in terms of rho 2, okay. So, can we express rho 1 in terms of rho 2? Can we? We can, right, because we can do a Taylor expansion. So, what it should be? I simply want to write rho 1 in terms of rho 2. So, it is rho 1 minus, because I am going down in the opposite direction. So, so what is going to happen? Rho 2 minus, I am not 2 equals minus, I just want rho 2 minus rho 1. I want my rho 2 minus rho 1, sorry, I do not think so.
It is somewhere.
Somewhere. Okay. So, I will simply substitute that. Okay. So it would have been great if there was a yellow chalk. There is, but this much. So this is my Bront-Weisler frequency, square of that. Okay. So this equation I will simply write again. Okay. This is my small displacement. Just to remember that n square is a function of z, and for simplicity there is no need to assume that n square is a function of z. You can assume n square as constant also, which is your very well known, say n square assumed constant. So simple oscillations, you know that this is the equation, right? It is absolutely the same, except that and you, since you are very close, you can you are doing a very small an analysis very close to this part, you can definitely assume n square as constant, because you have zoomed in a small region, right, in the ocean. So you can kind of assume that density d rho bar dz is approximately constant in that region, and you can do this analysis, and this is what you get, something of that sort. Okay. And n is buoyancy frequency or now this Weisler is probably from Finland, so he has a lots of dots over the, it's difficult to remember, but just I think except I, every vowel has 2 dots. Okay. So now you understand that if in a density stratified fluid a parcel is in a stable density stratified fluid. So in stable density stratified fluid, if a parcel is slightly displaced, it oscillates with frequency n. Okay. Yeah.
You are not considering any dissipative force, that's why it will go on oscillating, right?
Yeah, there is. So the assumption is that it is that there are no dissipations, or dissipations would work at a longer time scale. Yeah, obviously. Then if there is a dissipation, it will go down. It will stop. Obviously. So for example, when you are doing this spring mass system, if you don't assume a damping, it is just going to go forever, right? So for waves, for understanding waves, we do not actually put a dissipation unless something is important. We are simply interested in waves characteristics. We usually do not put dissipation in the first place. If you are really interested in, that's a different story. Okay. Okay. Now what happens if the density is unstably stratified? What happens if it is not like this, but the way it was in Professor Huppert's talk, say if the density is like this, will you have an oscillation? So n square is what? N square would be negative, right? I mean, this quantity will be a negative. You have to have a negative sign. If you have n square as positive, then it has to be with a negative, because n square is with what? See, n square is minus g by rho 2 d rho bar dz. D rho bar dz in this case is positive. Sorry, negative. So negative and negative makes it positive. But in that case, d rho bar dz would have been a positive quantity, and positive and negative would have given you a negative. So, this n squared is a negative quantity. So, that would give you exponential solutions, right. So, just like this gives you oscillations, but this gives you exponential solutions, it is just that. Okay. So, the next thing I would try to do is to understand more properties of internal gravity waves. Right now, I have just shown that the density stratification causes, if you give a small thing, it just oscillates. We will next go into the fact that these beams form. So, more into the internal gravity wave business. So, if you have any questions on this part, just ask me now. Where is my can I erase this? Is okay? Okay. Okay, so let's see what are the governing equations of internal gravity waves. So now we are into internal gravity waves. And in the last class, we know that it satisfies the continuity equation. Okay, I am writing with prime as a continuation of the last class. Okay. So, this is my perturbations, and because there is no mean flow. So, everything here is u prime, w prime, these are all perturbation quantities. So, this is my continuity equation, continuity. What about x momentum equation? We wrote du prime dt, which is del u prime del t plus u del u prime del x and who remembers why we can do this? We talked in the last what? Boussinesq approximation, yes. So, Boussinesq approximation has been invoked. So, density, so here otherwise you had rho bar plus rho prime, which you can take as simply as rho bar or whatever is a reference density rho 0. Boussinesq approximation becomes more important here. Actually, it is not technically the Boussinesq approximation. Boussinesq approximation becomes important is here. So, this is technically your Boussinesq approximation, right, that you are keeping rho prime. So, my rho prime and p prime are looking very similar. Okay. So, you have done this about a background state that is hydrostatic. Okay. Just like what we did in the last class, and this is what your Boussinesq approximation is. You, when it is multiplied by g, you keep rho prime, but here you have thrown it away, right, and that is what the rho 0 is. So, continuity x momentum, z momentum, and there was another thing, okay, which I just mentioned. Remember that continuity equation is divided into two parts, d rho dt plus rho divergence of u is 0. Okay. So, this divergence u is, so this one goes to 0 because density is materially conserved. Okay. That gives you divergence u is 0. Okay. That is this. So, we have actually not talked anything about this, although it was mentioned in Professor Huppert's slides. Okay. I will just talk about that. So, material conservation of density. So, this one, this row by the way is the full row, full density, rho bar plus rho prime. Okay. Obviously, I have not done anything here, everything else I have decomposed into rho bar plus rho prime, did the whole thing. For this one I did not touch it even. So, let me write this as ddt of rho bar plus rho prime xzt. Okay. Now, before I go into that, I just want to mention that now in this class we are interested in small amplitude things. Okay. We are not interested in anything that is non-linear. So, we will throw away any term which has non-linearity. Okay. So, these terms are all gone, gone. Okay. No non-linearity. We are interested in linear waves, small amplitude waves. Okay. So, if this is order epsilon, this has to be order epsilon square, and we are interested in linear waves up to order epsilon. Okay. What about this equation? It gives you ddt of rho bar plus ddt of rho prime. Now, ddt of rho bar is what? Del rho bar del t, which is 0 because rho bar is a function of z, plus u d rho bar dz dx plus w d rho bar dz gone, survives, and this one is del rho prime del t plus u del rho prime del x, non-linear, gone, non-linear, gone. Okay. So, what survives from here is del rho prime del t plus w prime d rho bar dz is 0. Okay. So, this is your continuity, call it 1, 2, 3, and I will call this one as 4. So, actually this equation was written in the slide. So, you have 4 equations and 4 unknowns, you can potentially solve the problem. So, you combine all of them, you get a single equation. I mean, it is slightly more involved to get them combined into a single equation, but what happens finally is what I am going to write. So, if you combine all of them, so combine equations 1 to 4 gives you something like okay. So, from now on I will not write w prime. Okay. So, I will simply write w prime as w. There is no point, because if I had a bar and a prime, I can continue to do that. It is no longer required. So, just assume that because w is small, you can simply assume w prime this plus n square, which by the way is a function of z, and that is why I am emphasizing that n square can be a function of z. There is no reason for it to be constant. Constant is a special case. Okay. So, this is my governing equation for internal gravity waves. Okay. And obviously, this is, there has to be an initial condition and boundary condition. Any questions about, I do not know what it is. Any questions about this?
Do you want to take it up?
No, it's okay. I'll have to show some figures, so that's why it's okay. Any questions about this, the entire thing? Yes.
Equation number 1 and 4 seems to be originating from the Continental Shelf, right?
Yeah.
One is the left part and one is
Yeah. Yeah.
we are still treating it as separate equations, then combining.
No. So, the first thing is the assumption that the flow is nearly incompressible. which is the basic assumption is that the dense. So see, for the Boussinesq approximation, what is the what comes first, that the density is materially conserved, although the density is varying, as we also came to know that it takes a long time to diffuse, right. So Professor Huppert gave up an example of this boiling thing. If you allow conduction, the same kind of thing, say if you have a reed diffuser and if there is no turbulence in your room, it would take few days for that fragrance to come to reach your nose. Okay. I mean, if you see, the simple scaling analysis shows that that is going to be the case, and that does not happen specifically for your, say, agarbattis and all, because there is always a plume coming up that causes some mixing. Okay. If now you put sugar in your cup of tea and you don't wait, you cause you need to stir it. So so obviously in oceans, whenever we have these parcels moving around, diffusion in a, I am not talking about the boundary layer region or some very specific regions. In general, diffusivities are not that important. Okay, it takes a longer time. It will become important after a longer time. Whatever the problems of waves and all, whatever we are mostly interested, longer waves, where it is not something which is the most crucial thing. Okay. So anyways, d rho dt as 0, which individually makes divergence of u also 0, because the flow is incompressible and the divergence free condition is satisfied. So d rho dt being 0 and this, so the one equation can give rise to two conditions. Okay. So one is this material conservation of density, from which you get this, okay, where there is a direct relation of rho prime with w prime. Okay. And the other is the continuity, what you get in general. Okay. See, otherwise d rho dt, if rho is constant, you still get it. It is something which is not very useful. D rho dt is 0, rho is constant. How useful it is? It is not useful. Okay. Here it becomes useful because rho is not constant. Okay. Things, so you take a parcel, the parcel moves from, so that was the interesting part, that it is moving up and moving down to some ambiances where the density is not the same, right. Okay. So the next thing we will try to do is, how many of you know normal modes? Probably most of you know normal modes. It was also discussed in last class. So you can assume a normal mode form. So small w can be written as, say, capital W z I k x minus omega t. Okay. Now the same thing you can take a Laplace transform. You take Laplace transform twice because the two time derivatives, and a Fourier transform in x, you should end up getting the same answer. Okay. Now obviously when I write this, it is implied that there is a complex conjugate there, which is important because that is going to make w a real quantity. We mostly do not write the CC because we assume that the audience knows. Okay. Anyways, when we substitute this, what happens to, can you just think that what is going to happen to that equation. So I wrote up to equation 1 to 4, call it equation 5, and we substitute this normal mode ansatz in equation 5. Okay. There are two time derivatives, so minus I and minus I, right. So what it will give? Minus omega, minus omega square. Is it true? Okay. And then what about del 2 omega del x square? Okay. Minus k square, and here and here call it W double Z. So, everything is multiplied by e to the power I k x minus omega t, but that is non-zero, you can throw it away. Okay. And here n square remains n square, I will still write n square z, and what about that del 2 omega del x square will give rise to minus k square w. Okay. So, please simplify it and give me it in some form, that is w z z plus something w equals 0. So, that is what you have to give me, and so we are doing this in this domain. So, this is my x, this is my z, and right now we are working with a rectangular domain. Okay. Now, this is my z equals 0 and z equals minus h. Okay. So, the height of this box is h. Now, you can say, why did I put the coordinate system here, why not here? I mean, it is a convention, it is not like you can put it very well there also. Okay. And your system is horizontally periodic. Okay. What about the top? Okay. You assume that the top is, it is an ocean, the top has to be a free surface, but there is an approximation that is always used. It is called the rigid lid approximation. It is as if there is a rigid lid, you are holding a rigid lid on the top of the ocean. Okay. I mean, at order epsilon, this makes perfect sense. At the higher order, whatever the wave I was showing, it is a manifestation at the higher order. At the first order of approximation, this is absolutely fine. Okay. So, your w velocity is 0, which gives you your capital W also 0. Okay. See, w velocity, the small w, which is the velocity has to be 0 at a solid, w velocity has to be 0 at a solid boundary because of the impenetrability, it cannot enter, right. So, w velocity has to be 0. So, small w has to be 0 here, and it is like a rigid lid. So, obviously, small w also has to be 0 here, which means the capital W also has to be 0, right. So, okay, please tell me what this good. So, you understand that we have reduced a PD to an ODE, right. So, if you have not realized, this is a PD and this is an ODE. Please tell me what this equation is. Are you getting something like this? So, this with the boundary conditions, W 0 is 0 and W at minus h is 0. Okay. These are all capital W, there is no more small w in the business. So, you understand that this is an eigenvalue problem. W is basically an eigenfunction, right. It is an eigenvalue problem, and so when can this eigenvalue problem be solved? I mean, when you have non-trivial solutions. Okay. What about these k square? K is what? It is a wave number, you know, right? Or do I have to explain what is a wave number? It is inverse of the wavelength, right? So, in Saturn, when you see it is like a hexagon on the Saturns, you have seen the picture, right? The Saturns in the north pole of the Saturn, you have the hexagonal polar vortex. If it is hexagon, it means that wave number is 6, pentagon wave number is 5. Okay. So, how many waves are in a certain region? It may not be a, so k may not be a, in this one k may not be a whole number, but it can be made into a whole number. How many of the waves in a unit length, okay, or in certain length? I mean, if you are if you have already chosen that this is L and this is your entire thing, it might not be a whole number, but for Saturn it is. Okay. So obviously you need, so k square is obviously positive. I mean, k being 0 does not give rise to an eigenvalue problem, and the other thing is n square by omega square minus 1 has to be positive to have, I mean, any eigenvalue solution, eigenvalue problem to be going, otherwise it will be an exponential solution, right. And think about it, if it gives rise to exponential solutions, it will be either exponentially growing or decaying. But the fact that w equals 0 at the boundaries, what it is going to make it? It is going to make the solution 0 everywhere, so it is not even a solution. So the only possible solution would be when n square by omega square minus 1 is a positive quantity, right. So waves, I mean, so that is important, I mean, that is very important, because what does it mean? See, omega, say, so omega equals to n times a number which is less than 1, right, has to be a number less than 1. Okay. We will come into that, I am just writing it nicely like this because we will come into that. So omega by n is a quantity which is smaller than 1. Not all frequencies, so we remember that so what you can do, that particle we displaced it a little bit and it oscillated, right. What you can do, you can hold the particle as if, and you can cause it oscillate, make it oscillate. Okay. Say if you make it oscillate like this, if you oscillate with, it depends on the frequency of oscillation, it is not like for all frequencies it is going to generate waves. So if you, there is a famous experiment, it is what they do, if you have a density stratified fluid, okay, and you put a pendulum, a bob or something, and you cause it to oscillate, okay, like this, you cause it to oscillate. So once you cause it to oscillate, it gives rise to internal gravity wave beams, okay, like this. And if your omega is too large, then you will get you will get decaying solutions, you won't get anything, you will get evanescent solutions. So you cannot force with some frequency which is too much, okay. N is the buoyancy frequency, yes. So as long as this condition is satisfied, you get these internal gravity waves. So these are internal gravity waves. So as long as this condition is satisfied, okay. So you will see that omega equals n something will come as cos theta, and that theta is the angle of the which it makes with the beam makes with the horizontal, okay. That is why I have written it less than 1. So omega cannot be, so if you oscillate with a very high frequency, nothing is going to happen, okay. So in oceans, who supplies you omega? Tides. Tides cause these things to, and so no one is actually holding a pendulum and causing it to oscillate in the ocean to generate internal gravity waves, okay. So the pendulum is like a mountain, and you do not oscillate the pendulum, do not move it like this. It is a tide that goes to and fro, that is the same like this, right. So the tides go like this, and the tidal frequency is like 10 to the power minus 4 per second, okay. N in the oceans goes like 10 to the power minus 1 to 10 to the power minus 3, depends, okay. But usually n is less than omega, and that is why you get internal gravity waves. In the regions where it is greater than omega, you won't, okay. What happens if n is 0? N square is 0, the equation does not look valid. because you cannot get an internal gravity wave when there is no density stratification, right. Okay. With that, so let's go into this business. I am just erasing this, you understand, right. So, another important point is usually you put you assume that omega is a positive quantity, frequency take as positive. Okay. Now, you have to separate between rightward propagating wave and leftward propagating wave. Rightward you can call it k and the leftward as minus k, say. The equation does not, I mean the equation is symmetric because it is k square, right. It is the same if you put k or minus k, it is the same thing, right. So, that is one of the important points to remember, okay, the k symmetry. Another thing we will just, so this type of equations we have done before, right. These are called Sturm-Liouville boundary value problems. Let me first talk about the more difficult problem which we are not going to solve. Again, I would mention that I will just write a small a z here to keep on hammering that n square may not be constant, the density stratification may not be constant. Okay. Now, I am just let m square, I will just write this case right. So, what happens if you have an equation like this? Can you solve an equation of this form where m square is arbitrary, an arbitrary function of z? Can you solve this equation? So, these are all something like Schrodinger's wave equations. Okay. Okay. In general, you know even that what about m square z being z? Can you solve that? See, in this class we are not going to go into that, but what about m square z is not a constant coefficient, it could be, right. In general the ocean is density stratified, non-uniform stratification. So, m square z, what happens if m square z is something like z, some constant times z? Can you solve that? You can, right. There is something called Airy function, you have seen Airy's equation. So, there are classes of I mean those are not, you do not get an exact solution, you will get a series solution. Okay. In general, when the density stratification in the ocean does not vary very rapidly, we do something called the WKB approximation, and it gives rise to asymptotic solutions, which again I am not going to do, but say the density stratification, if it is not like this, that is too fast, people still use it, still uses WKB because that is the thing that's all you can do. Okay. But it is not that accurate. Okay. But if the density varies like this, it will be more accurate. Okay. So, when we have nothing else to do, we will do it, we will just assume that it is not accurate, that much accurate. Okay. However, we are not going into this variable density stratification. I am just putting it as making it a point that any equation of that sort, you do not have closed form solutions. Okay. In general, you do not have closed form solutions. So, let us go back to this equation and try to solve it. So, now we know that this equation does not have a closed form, there are some approximate solutions WKB which is applicable. We will now go into the simpler thing, which is m square is constant. Okay. That is all we know mostly, and now we will try to solve it. Can we solve it? Obviously we can, right? So W would be something like A sin mz plus B cos mz subjected to the boundary conditions W 0, W minus H is 0. Solve it for me. What is B? What B turns out to be? 0. Okay, good. So this is gone. And what the first part is going to give you? What the other boundary condition is going to give you? Speak up, speak up. What equation? No, you are saying something, you are doing well, just speak up. Series solution. Yeah, I mean it is going to give you, so just put, so this is Wz, W of minus H is A sin minus mH, which is 0, okay. So it should give you sin mH is 0. So mH is n pi, okay.
Sorry to interrupt. Why have we put W0 on n equal to H?
Huh?
Sorry, the top why W equal to 0.
Huh?
Top.
Huh?
Rigid lid.
Rigid lid boundary condition. Yes, because at the order epsilon, rigid lid is I mean, so about the free surface enters at order epsilon square. Anything on the free surface, the fact that internal gravity waves actually hit and do produce something, it cannot produce it. It is technically not a rigid lid, but at order epsilon it is a rigid lid. I mean, so we have neglected the small terms. So I mean, if it is just a smallness parameter, you can think of steepness. Usually we take it as steepness parameter, say Ka.
In that picture,
Huh.
epsilon is a ratio of what two things? What is the small?
So that's what I mean. So usually we take epsilon as Ka, where A is the amplitude of the wave and K is the wave number. So usually the nonlinearity is somewhere. The measure of nonlinearity usually the steepness. So yeah, usually it is the, so epsilon being small, so A by K, A by lambda is much less than 1, or A is much less than lambda. Huh.
So for long waves, the rigid lid is same as the free surface, more or less to leading order.
A rigid lid is nearly equal to the free surface to the leading order, yes.
Can I just add one thing just behind this? The frequency of the internal wave that we're talking about here is very much less than the frequency of free surface wave.
Yeah,
And that's really
yeah.
the justification of the rigid lid approach.
Yes, the free surface waves obviously. So the one which I was showing is a particular, I showed a video where the free surface also travels because of this. It's just the order epsilon square response. So what you are saying would be the is the natural response, that is a particular solution where the free surface has some undulations but travels like that. So this deformation keeps on traveling. But yeah, I mean the other thing is that the frequency, the surface gravity waves travel very fast.
Yeah.
So that would so at the if it was an interfacial wave, then definitely we would have to take that. I mean it is air water, that's why we can make certain approximations which would not be valid if it was, I mean, water and so glycerin and water or something. I mean if the density ratio is not that much, it is probably the rigid lid is not going to be valid. So for example, we do not apply a rigid lid boundary condition if you take rho 1 and rho 2. So rho 1 and rho 2 are not that different, and you have a density like this, and you cause it to, so the beams to hit there, you don't really apply a rigid lid boundary condition, it's a free surface boundary condition. Okay. but here if the density is far different, then it is a different story, okay, because you know that the disturbance it is going to produce is very, very small. Okay. And a lot of it has to do with absolutely, as there comes a ratio between the surface waves and the internal waves in the square, c square by c surface gravity wave square, something like that comes, and then I mean it is an order of magnitude that so it's somehow like your w velocity, it turns out to be w if you expand plus epsilon w1 whatever it is like this. So this usually it is like also c c internal gravity wave square by c surface gravity wave square, which is a very small quantity, you can throw it away and it turns out to be 0. So w0 is 0 at the leading order, okay, plus something. So free surface work, I mean the rigid lead boundary condition works very nicely for these kind of situations, okay. If you want, I actually have the derivation for this in a paper, I can show it. Okay, so the coming back to the problem, we know that mh is n pi or m, and what turns out to be m is basically when you are writing this equation as m squared w. If you have an equation like x double dot plus omega square x is 0, this is the frequency. If you write this as this, it is the wave number, right. So m turns out to be the vertical wave number, okay. So what does it mean that m as n pi by h? So you have n equals 0 is not a solution, right. It has to be more than that. So that is this is the first mode, okay, and you can keep on going. This is the second mode, and you will have something like this as the third mode. So n equals 1, 2, 3 and so on, okay. So there is a quantization, because only the integer, as you can see mh is n pi, I mean this quantization it is naturally forced. Right. Now we have to write the dispersion relation, and the dispersion relation, so remember that m square is this. You know what dispersion relation is, right, most of you. So the relation between frequency and wave number is called the dispersion relation. So for sound it is omega by k is constant, okay. So we will simply write the dispersion relation is just this, whatever we have assumed. This is your dispersion relation because m is your vertical wave number, okay. So m square is k square. Remember that now n square is constant, otherwise it is I mean it is a relation, this one makes you a right dispersion relation. Okay. So Ishan, what you were asking, this is one of the things which we did. This is the surface signature, this is at the free surface, okay, and this is at order epsilon squared. These are not so called surface gravity waves, they do not move so fast. They are simply these red, the blue, red, blue, this thing, whatever it impinges, that density, that keeps on moving with the frequency of these waves. Okay, it's like
I guess that's a transient problem. While what you are doing with steady state,
which one?
the one that you are doing right
No, this is also a transient problem. What I have done is I have converted my equations into k omega space.
now, it's not transient because there are no initial conditions.
Oh, yeah. So in this one, yes, I have not put any initial conditions. Yes.
Looking at the long time,
Yeah.
so
Huh.
the reflection thing is not really there.
The
What you are showing over there
Huh.
is that you are putting a perturbation somewhere.
Right.
And the internal gravity waves are traveling and then impinging upon the free surface or rigid lid or whatever it may be.
Yes.
So that is a genuinely transient problem.
This is a transient problem with this simulation is a genuine transient problem. This problem, if I go into expand to order epsilon square, I can still include the free the moving the moving of the boundary.
I guess
Huh.
I was only wondering as to how good or bad
Huh.
rigid lid approximation is for surface of the sea.
It is a very good, it's a definitely a very good approximation. Yeah, at order epsilon it is great. So this is one of the things which I really want to show you, and this is what I'll talk about a little bit. So you understand, I'm just erasing something, just the final answer, the most important results I will just write. It is very cluttered now. So one thing is your equation is like WZZ plus m square, which is now constant, W is 0, with boundary conditions W is 0, right, and the solution of this is, it gives you, so what kind of W's are allowable is W is sine, we got A sine mz, A does not, it's an eigenvalue problem, eigen solution, it does not matter, mz, right, that is the allowable solution, with m being not anything, where m equals, you have n pi by h, right. And remember that m is given by this. Okay. So that's kind of a summary of all those whatever it is. So I'm going to erase this board. I don't have too much time though, but let me choose then. Okay, so let me substitute this here, right. So instead of writing k, I will now write with a in fact, before I substitute, there is something important I want to tell you. Let my wave vector be k. Okay. So this is my k, small k and m. Okay. This is my wave vector. Wave vector means the direction in which the phases travel. Okay. So so assume that this is my crest and this is my trough, again crest, trough, and so on. So it's like an asbestos going like this, you are taking a top view. So this is your trough, this is crest, and so this is the direction of k, okay, k vector, okay, and say this angle is theta, right. So see that, so what is m by k? I just take m by k and I see that m by k does not depend on the so called mode number. See, m is n pi by h, something like that, right. There is no dependence on small n here, okay, which means that the vertical wave number and the horizontal wave number are in a particular ratio which is independent of n. Okay. This is one thing. The other thing is, let us write this one as n square pi square by h square is k n square something, right. This is the nth wave. This is the wave number corresponding to the nth mode. So, what is the first mode? If you have forgotten, n is 1, looks like this, that is the first mode. The second mode would be like this, the second mode, and so on. You can keep on increasing, right. Those are the modes. So, here n square pi is k n square times something. Some other mode is L square pi square by h square is k L square times the same thing. And what is this thing? I will just write. Right. If you take the ratio k n square by k L square, it is n square by L square, or k n by k L is n by L. Okay. Which means that, see, n and L are numbers, are integers, right, natural numbers which you saw, right. So, it means that it is going to be a rational number, the ratio is going to be rational, and the more important point is, I mean, the periodic structure is always maintained. Say, take L is say 50 or something. So, this much takes 50, this much also takes 50. Okay. So, they form this. So, this periodicity is maintained. That is one thing. The other thing is the wave number that m by k is independent of the mode number n. Okay. So, the question why I am saying this is something which is very interesting for internal gravity waves. It's a fascinating thing. The phase speed, the definition of phase speed is c equals omega by k. Okay. Say I will judge the phase speed in the x direction, and omega by k, if you just do that omega by k, you will see that it is proportional to 1 by n, which means that this wave is travelling faster, this wave is travelling slower, and the more and more like this, it is travelling very slowly. These modes are travelling like that. Okay. Someone is travelling faster, someone is travelling. The whole idea is that the low modes travel faster. That is very important for oceans. Okay. Now, things travel at different rates. However, this picture you are seeing, or whatever the video I showed, a certain structure remains preserved. How can it happen? Okay. See, a combination of these eigen functions are going to give you a structure, the whole structure. But somehow that structure is getting preserved, although the individual phase speeds of each are different. How is it being possible? Is because it is not only a one direction problem, it is a two dimensional problem, and it turns out that omega by there are two of these, that they maintain this ratio, and the second thing is that this m by k, take any wave, vertical and horizontal wave numbers are independent of n, right. M by k does not depend on n. If you take m and k, take the ratio, it always propagates at this angle theta, right. M by k is n square minus 1, n square by omega square minus 1, which would be something like a cos theta or something tan theta, tan square theta, whatever. So, that angle is preserved. Take any mode number. Mode number 100 is going to preserve the same, make the same angle, travel at the same angle as any other wave number, as mode number 1. So, everyone has this as a wave vector, and that is why this kind of a thing is preserved. So here it is a it's something like you just show one mode, just think of this part I have made it, 2 modes, 3 modes, more and more modes are added, and this thing becomes sharper and sharper and sharper, okay. And that is very very interesting for internal gravity waves.
Sorry, what was omega? I think
Frequency.
frequency of.
So it is a frequency of the internal gravity waves, e to the power I omega t, whatever the.
What is m is the wave number, right?
M is the vertical wave. So there are so this problem has 2 wave numbers.
I guess
So if I substituted e to the power I k x, I did not assume
so for a given frequency the theta is that what you are saying?
for a given frequency, yeah. So it turns out that for a given frequency and a given density stratification,
Then theta is fixed.
theta is fixed.
So basically, so in a driven problem,
Huh.
for example, the tides are driving the internal gravity wave. So omega is that of the tides.
Omega is that of the tides. Yes, absolutely.
The theta gets fixed.
That's why the theta gets fixed. Yes, absolutely. Omega is determined by the tides. Yes, yes.
You could have any theta depending on the choice of omega.
Yeah, absolutely. So omega, given that, so omega is the whatever this frequency is, forcing frequency is, it diurnal tide could be the semi diurnal tide, whatever you force it, or you can make this like go like that, right? So that is so omega equals n cos theta, which makes a very important point that and this cos theta is not is just that I'll write. So cos theta is basically right. Now usually when you write a dispersion relation, it is frequency with respect to wave number. So frequency changes with wave number, right? Here frequency does not change with wave numbers magnitude, okay. So change the wave number k, make k as 20, okay. The m is somehow chosen in such a way that m by k remains the same somehow. So it is in other words, I would say that if omega is fixed, your direction of propagation is determined, okay. It is not like you have some other wave that is going to change its angle, right. All waves are going to propagate at a certain angle, and that is why you get this, all waves would propagate at a certain angle, okay. All waves have the of the same frequency, because you are assuming that you are exciting them at the same frequency. Yeah,
The problem was solved not as a forced problem, it was solved as a free vibration problem.
is a solved with a free vibration problem. Yes, yes.
In the end you are connecting it to a forced vibration.
Force vibration problem. Yes, yes. Okay, one small thing before we finish. I mean, internal gravity waves are just extremely amazing. The other thing, which is, how many of you know about group speed? Have you ever heard about group speed? Phase speed you have heard, group speed, okay. So group speed is the speed with which the packet travels, wave packet travels, and it is the speed with which the energy propagates, okay. So one interesting aspect of internal gravity waves is, so again I am drawing, let me go back here. This is the direction of group, okay. Do you know which direction the phase travels? Phase travels perpendicular to the group, okay, which is very very different from what you mostly understand, mostly know. Say for example, surface gravity waves, phase and group are same direction. Sometimes it can reverse the direction, that there is possible. If you have flow, it is possible, but just perpendicular to it is something which is very very interesting for internal gravity waves. It happens to be the very similar for something called inertial waves, which are because of rotation of the earth, okay. So these two have very similar behavior. So I will just make it a point that phase speed, so phase speed you have is omega by k, right. I would just put it as omega by k, and group speed. So, del omega del k, right, and which one?
If k is a vector, then it's a velocity. Is that underlying for a vector?
Yes, yes, yes. So, I mean I am just writing it. So, so turns out that if you have k dot, if you write del omega del k, so as it's a grad operator, basically grad operator, right, k dot grad k turns out to be 0. It is not simple to prove, not simple, it's a tedious exercise, but I have found a way to prove it which is very short, and I will just give you as homework. You can try it. I mean, it is something which we learned in the first year. It's called Euler's homogeneous function theorem. Okay. Otherwise, it is painful. It takes time to prove it. Okay. So Euler's homogeneous function theorem, I just thought of writing it. So do you know what a homogeneous function is, right? So say f of t x, f of t y, you can write as t to the power r f of x y. Okay. So it is of order r. Then if that is the case, then turns out, so for any t, this is valid for any t, this x dot grad f is it is r times f, I believe. So x dot grad f is r times f. After substituting t equals to 1, it turns out, it comes out. Okay. So this is a standard, this is known. You can use the same as k and grad f as del omega del k. So here all you have to use is f as, so I am also giving you the how to do it. F is omega, k and m. Okay. X is k, y is m. All you need to prove is r equals 0. That is all you need to prove, because x dot grad f, which is k dot del omega del k, has to be 0. So all you need to prove is r equals 0, done. Okay. Why k dot del omega del k? Why? So I said phase speed and group speed are, I mean, they are like perpendicular, because phases travel in the direction of k. That's why. Okay. It is the order of homogeneity. Okay. So I gave you the relation, right? That k and m relation. Okay. Just put, instead of k, right, put tk, and instead of m, put tm. See what r comes out to be. That is what you have to see. You will see that it is t to the power 0. So this 0th order, that you will find out. Okay. So here I will finish. I don't think so, but anyways, I will take that. Thanks. So you understand that you how to write it. It is a simplified thing. I have, so it is omega k hat, and I have write as a mod k square and all. So I just wanted to have a parity. That's it. And grad, you understand that this and grad are the same thing. I believe you understand, right? Or, I mean, this is basically a grad. So it is grad omega, but it's not with respect to x, with respect to k vector. That's why the understandable, right? Okay.